All right, so guys, vectors in a plane. Let's talk about the basics of a vector. So good physics kind of explanation. So like speed versus velocity, okay? What's the difference between speed and velocity? Velocity has direction and magnitude. Speed, just magnitude. So if you want to be a smart ass, we get pulled over by the cops on El Camino. Let's say, for example, you consider southbound to be the negative direction. So let's say you're going from Redwood City to school and you're running late to school. And this, what's the speed limit? What's the speed limit in El Camino? Which is like right around like Chavez Market or Target, about 35 miles an hour. Okay, good. So let's say you're going 50 miles an hour, which is not good. It's not safe, right? But you think it was negative because you're thinking velocity, right? So you tell the cops, wait, but my velocity is negative 50. It's less than 35. They're gonna still give you a ticket for being a smart ass. So don't use that as an excuse. Just apologize and pray that you don't get a ticket. But the point being is that speed doesn't have direction, right? Whether you're going north or south, that's still very dangerous, going 50 miles an hour, right? But velocity has direction, depending on what you define as positive or negative, right? So if southbound is negative, then that would be like negative 50, and north is positive. So if you're going like towards Road City or San Carlos, it'll be positive. So that's what's meant by a scalar versus a vector. A scalar is just a number, but a vector has direction combined with it. And that's why in physics, for example, if you're doing two-dimensional like projectile motion or force diagrams, which you guys might be doing in physics, sophomores I know are not doing that right now, but it's just good to be able to have that breakdown. Oh, it should be in the notes. You don't have it, David? It's additional notes. So, David, you have the ones from yesterday. So you have to get the new ones. Do you see it, David? Okay, cool. All right. So given PQ, so here's how you'd write it, guys. Quiet, please. Thank you. So think of geometry, guys, like a ray. P is like the endpoint, and the ray goes towards Q. Sometimes we actually put Q right at the end here also. Sometimes people do that. So that's considered vector PQ. The notation, you can write like this. P then Q with a little arrow like that. Let's say I call this AB. So that can be written like this. Now you could also use a shorthand notation if you want. What if you call this whole thing vector U? You call it that also if you wanted to. Some people just use a single letter to represent a vector. Or say I call this like V. U and V are very popular notations for vectors. So you can call that V. Just various notations you guys can use. This obviously is my initial point. And that, of course, is my terminal point where it ends. Now the length of the vector, that's kind of an interesting one. So the length of a vector is magnitude. There's a notation for that as well. So it's just simply how long it is, right? So like, if you're like got a ruler and measure it, it's how long it is. That's called magnitude. It's kind of a weird symbol that's used for that. Let me change colors for a bit of contrast. It's like a double absolute value, if that makes sense. Or you could do it like this. So just so you're familiar with the notation, it looks like a double absolute value, and that means distance or length. And for the other one, you'd write like this. Now, for those of you who are juniors, most likely you'll do AP Calculus PC next year. And then when you go off to college, you'll probably do multivariable calculus. And then you do something called vector calculus. So for those who are looking to do a STEM kind of major like engineering or something that's just heavy STEM related, if you're going to go econ or something that's non-engineering, non-math, you don't have to. But vector calculus is another branch of calculus you might have to take. And you have to get used to this notation. And it's it's been so long since I've done it, so I don't know what that's like anymore. But that's you got to go know the notation, right? So vectors have that have the same magnitude and direction, just so you know. Vectors that have the same magnitude and direction are considered equivalent vectors, just so you know. And to find the magnitude, a lot of it's going to involve Pythagorean theorem or distance formula, just so you know. We'll do that in just a moment. Okay, so that's some of the basics. Let's look at the one right below. Let U be represented by the following line segment directed by P equals 0, 0, and Q equals 3, 1. Let V be represented by the following: R equals 2, 2, and S equals 5, 3. Let's draw these below. All right, so let's do the PQ in blue. So I'm going to start here, and 3 1s right here. That's my vector. Just looks like that. Very simple. Now let's look at the next one. Where does that start? 2, 2. And going towards 5, 3. Okay, just some observations. What do you notice about these two vectors? Just some random observations. Same slopes, they're parallel. Totally right. Okay. Probably the lengths are the same also, I'd say. Yeah. Yeah, I'd say the lengths are probably root 10 each, right? Okay, cool. So we'll call this vector U. We'll call the red vector V. And if you're like me, you gotta be really careful with the handwriting because it can the U's and V's could easily blend, so be careful there. So because I drew it, awesome. And I think that's all we really had to do. Yeah, just draw it. So okay. And then another thing we need to talk about too is component form. Okay, so vectors can be expressed. So how do you express vectors? You express them not parentheses, kind of weird. Actually, they'll show it here. I'll have to draw for you guys. Now, what does that mean? And I think on the next page we'll get into that. Actually, I'll kind of talk about it right now. When we talk about it right now, it's just so you guys are not confused. So let's look at vector U. Actually, let's go back to blue. We'll color code this. So how can you express vector U in a different way, as opposed to just giving me 2 points? Like I know it starts at 0, 0, and ends at 3, 1, right? But how can I write that in a different way? So you could write vector U like this. Or some textbooks will write like this. If you have like an older sibling in college, you'll probably been taking vector calculus. And then for vector V, let's go back to red. Let's color code it. And then we're going to just kind of simmer on this a little bit, just to help you guys understand what's going on. Okay, some of the college math is coming to play here now. Okay. So these are not parentheses. These are not brackets. I'm not sure what you call them exactly, but these look kind of like triangular in a way. Or also like inequality symbols a little bit. So when you do vector notation, the first number is the horizontal component. The second number is a vertical component. That means that it's like a rise or a run thing. Think about it. It runs 3 and rises 1. It's run or rise. Exactly. Or here, some of these I and J. I is not a variable, mind you. It's not an imaginary number too. It's just a notation, just to say that, hey, the horizontal component of this vector is 3. The vertical component of this vector is 1. Now look at the red vector. It didn't change. Why is it exactly the same components? Say, go ahead. It's not the same run in the same line. And the same distance as well. And we just said earlier, when they have the same direction and have the same magnitude, they are equivalent vectors. Even if they start as different place, it's simply a translation of the vector. Did the vector get stretched? No. Did it get dilated or flipped or whatever? Like those geometry things I always remember doing geometry honors. I don't know if you guys did transformations. Our course we talk about transformations out too. But no, it just got translated. So it's still the same direction and magnitude. And how did I compute 3, 1? All you're doing is you're subtracting the x's and you're subtracting the y's. What's 5 minus 2? 3. What's 3 minus 2? 1. So in order to determine these components, all you have to do again is look at the run and rise, or simply subtract the x's and the y's. So like this, the difference in the x's here is 3, the difference y is 1, likewise in the red vector. And then we write it like this: u1 comma u2 or b1 comma b2, and we do these little triangular bracket things that make sense. So yeah, that's kind of what's happening. So we're just kind of giving the vectors 101, right? Just the basics, the fundamentals here. So now, do they appear equivalent? Yes, they do. And we know this because they have the same direction, same magnitude, right? So 2 ways to show. Same magnitude and direction. Or let me rephrase that. Write each vector in component form. By the way, when you find magnitude and direction, magnitude is going to involve distance formula or Pythagorean theorem. When you find direction, we're going to find theta. There's going to be a theta component to this, an angle. And it's going to involve tangent, by the way. We're going to be doing tangent. Tangent theta is going to equal y over x, right? From the unit circle. Theta is the inverse tan of y over x. So all ties back to trig. That's why we spent so much time on trig in the beginning of the semester. Okay. So in this case here, let's say you have P1, P2 is your initial point, Q1, Q2 is your terminal point. What would your vector be? It would simply be this. You'd write like this little triangular thing. Q1 minus P1, comma, Q2 minus P2. So it's terminal minus initial. Terminal minus initial. So again, what we had on the previous page, U was simply 3 minus 0, comma 1 minus 0, 3, 1, or B okay. It makes sense, right? Just, I just already talked about a few minutes ago. So the magnitude of vector U is simply going to be the square root of each of them. So you just do this. You simply take U1 squared. And the reason why that works is because you're already doing the difference in x's and y's, right? So this is U1, by the way. And that's U2. That's U1, and that's U2. So you've already done the difference between the x and y's when you take U1 and U2. So remember, this is U1. That's U2. And yeah, just Pythagorean theorem. That's all you're doing. Let me readjust screen here. Okay, let me shift this up. Okay, unit vector. A unit vector is a vector with a magnitude of 1. A zero vector, as you guessed it, is the same thing with a magnitude of what? So in this case, it's just a point because it has no distance, right? Just gonna be a dot. It's kind of weird. But unit vectors are very common and very popular. We tend to see those often. A unit vector, just so you know, I'm gonna just tell you what to expect from that because we will revisit that. It's simply when you take hold on, Zaid, the vector itself and you divide by its magnitude. Because that will force the issue that will have a magnitude of 1. That's how unit vector is done. Is that your question, or you can answer a question, or
So it's not these, well, I see a lot of similarities between just like document and finding difference. What's the point exactly of that?
physics? Physics. That's the really big reason why. Especially when you're looking at like Fort. Are you junior or sophomore? Sorry. Okay, so for who's in AP Physics right now? Okay, have you guys done force or free body diagrams yet? Okay, you guys using vectors? There we go. Yeah, like you have to look at like the horizontal and vertical components. You got to break it down. You got like like normal force. You got to look at mass due to gravity, apply force. Yeah, so it really makes physics much more manageable when you have vectors. So, especially if you get into like engineering disciplines, it's big time there. All right, anyway, let's find the vector here. So vector v is going to be -1 minus 4, 5 minus -7. Okay. So you get -5, comma 12. If I plot the points, easy to do. So my eyes got easy. Hard parts, my eyes, 5, 6, 7. I think right there. That's where it starts. Then 1,5, kind of ballparking it a little bit. My magnitude is simply Pythagorean theorem, right? So when you just do the square roots of each of those components squared, -5 is your horizontal component, 12 is your vertical components. You get root 169, which of course is 13. That's the length of the vector. And that's my vector and component 1. Okay. We're cool so far? You good? Let's see. We got till 125. Okay. Let's keep moving. I think we can move a little faster now. The math that goes into it is pretty simple. It's not that hard. A scalar multiplier is like distributive property. So think of it like this. Distributive property. Really not that much different than distributive property. So if you got a k in front, so you got a k in front of like v1 and v2, whoop-de-doo, just distribute it. That's all. That's all you gotta do. kv1, comma kv2. That's all. So it's not that hard. If you have a 2 in front, double it. If it's negative, then flip it. By the way, if it's a negative in front, it does flip the direction. So if it's going like this, it goes the other way now. It goes opposite. It turns around. So you're doing 180. Hence, like if you said southbound is a negative, like again, you're going from Redwood City to Sacred Heart, you're going -50 miles an hour, then it's +50 miles an hour. No, we don't. It's all bad because you're getting accidents, the same impact. Yeah, good. By the way, have you guys done momentum yet in physics? Yeah, so in that case, you're looking at mass times velocity, but it has direction. But when we look at the impact, well, okay, we could talk time physics. Yeah. On momentum?
Yes.
Good. If you have questions, ask. I'm more happy to help you guys. All right. All right. Vector addition. Very simple too, guys. We call it the resultant. It just means what results when you add the two vectors. So it's very simple. When you add the two, you're going to do u1 plus v1, comma u2. Now they're using v's trying to blend, right? Gotta be awful careful here. U2 plus V2. The negative of it just goes in the opposite direction, right? Everything reverses. The difference, same thing, just subtract the two, right? The arithmetic is incredibly easy here. But trust me, vectors can get a little wild as you get deeper with them down the road. Okay. You could also add vectors using parallelograms. So, but questions so far on this before I get to the drawing part. Okay, actually, before I show you the visualization, let's do example 3, and then I'll give you a general way of visualizing the addition and subtraction of vectors. Yeah, what's up?
Yeah.
Hmm?
The last line.
The difference?
Yeah.
I subtract, that's all. I'm subtracting 2 vectors. Minus?
Oh, well, because you. It's just subtraction. Yeah.
You're overthinking, dude.
Yeah.
Yeah. All right. So let's, before I do the visualize vector addition subtraction with the parallelogram law, let's do example 3 just so you can see what's happening. So you use this. Now, here's the thing. If you're not given initial internal points, assume initial point is 0, 0 for one of the vectors. Let me get a chance to copy that down first. Okay. So you're given vectors U and V. But I did not give you the initial terminal points for each one. We did that previously, right? Previously, I gave you initial terminal points for each one, and we had to find the vector. Now you straight just hey, here's the vector in component form. Vector U has a horizontal component -1 and vertical component 3, so it's going 1 left, 3 up. This one's going 4 right, 7 up. But I didn't give you initial points. Force the issue of 0, 0 as the initial point for one of the vectors. Let's say we'll focus on vector U. Let's start that at 0, 0. Okay, so if I start that at 0, 0, then where's going to be the terminal point, guys? -1, 3. Yeah, make it easy for yourself, right? Okay, we're good so far? Okay, that's vector U. Now, vector V. I can start at 0, 0. But it doesn't help me too much because what I want to do is I want to connect these vectors. We're adding vectors, very important. Let me add this as a text box. When adding or subtracting vectors, gotta stop throwing stuff, please. Thanks. You need to connect the head of one vector to the tail of the other. No, there's not. Well, unless you're subtracting, it will. We'll see. We'll see in a moment. Okay. Which part, Thomas?
This part, no, if not given.
If not given initial terminal points, assume initial point is 0, 0 for one of the vectors.
What about the other one?
We'll get there in a moment. Just wait. Okay. So when adding and subtracting vectors, you need to connect the head of one vector to the tail of the other vector. So the second vector now, which is 4, 7, I could force at 0, 0. But guess what? If I put it at 0, 0, both tails are connected. I need to connect tail to head. So what you do, I'll do this in green. Actually, I'll do it in pink. I'll do it in pink. Ah, come on. So you're going to pick up from where the last vector left off. So my initial point here is negative 1 comma 3. So now let's go 4 right and 7 up. So go 4 right. What's 4 right, negative 1, guys? And 7 up from 3 will be 10. So I'm gonna go to 3 comma 10 now. So we're here, then 4, 5, 6, 7, 8, 9, 10. Because I'm gonna let it, because I have to connect from head to tail. Head of one vector, head of u to tail of v. So I'm putting the tail of v at the head of u. Where's the head of u? At negative 1 comma 3.
Because that's what that says.
Exactly. So now that's gonna be the tail of 4 comma 7.
So then from here, you just, so then what's the?
Does that make sense, guys? Did everyone catch that? So whatever this is, this now becomes the starting point for the next vector. That was the spot. So the terminal point of the first vector, that becomes the initial point of the second vector.
And what's this?
That's you. Oh, well, that's just a symbol. That's just notation.
Oh, I thought that was a line.
That's just simple. That's a symbol, guys. Yeah, guys, that's just notation. I know this is all brand new stuff. I know the notation's funny. So that's vector u. Correct. Okay. Now u plus v. Okay, and again, for those who are in physics, when you guys do like normal force, mass times gravity, you're trying to break that down. You do something kind of similar here in some ways. U plus V. Okay, that's called the parallelogram law. Because what you're doing is you're drawing the diagonal. Because what happens is that when you have a parallelogram, right? As you guys know, parallelograms look like this, right? If you draw, I guess a terrible looking parallelogram, my apologies. If that's U and that's V, the purple is U plus V. Because think about, what if I add U and V right now? What do I get? I get 3 comma 10, right? Of course, that's what U plus V is. 3. But what's happening, look at the black vector. The black vector starts at the tail of the first one and ends at the head of the second one. Does that go 3 right and 10 up? Yes, it does. That purple vector notation matches with this one right here. So yes, Adam, it's very simple, but you got to visualize it too. And the way you visualize it is you connect head to tail. Head of the first vector to tail of the second vector. So in general, excuse me. Now in general terms, what happens is this. Speaking generally, if I have U and I have V, then the combination of it is that. Okay. That's how you do it. And sorry, those will see little arrows. My little arrows suck. My apologies. Uh-oh. What's going on here? Okay. Okay, why is it doing that? Okay. All right, then for subtraction. It's a little funny for subtraction. Hey guys, quiet please, thank you. Okay. If you're subtracting vectors, this is a little tricky, guys. If you're subtracting vectors, it's the same thing as saying U plus negative V. You're multiplying V by negative 1. So if that's vector V, right? It's going this way. What would the negative be? Be flipped. Yes, exactly. I got to rotate that. So now it's going to look like this. So that's where the arrow is. And then the connection over here Yeah, but we want u minus v.
So you find negative v and percentage of u.
Yeah, yeah, as long as you connect head to tail. Very important. Connect head to tail. So it's the same thing as addition, but you got to reverse v and it's still connect head to tail. And we'll see some examples in just a moment. Let's look at part C. Oh, no worries. Okay, let's keep moving, guys. So really quickly, if I do 3u, that's simply just going to be 3 negative 1 comma 3. Or here, that will be negative 6 comma negative 1. Yep. Okay. I'm not going to do the drawing in just a time, but you get the point. Like you're extending it 3 times, or you're extending 2 by twice, and then you're doing v in the opposite direction. You're just connecting them. But we'll just move on to parts. The next part. Because I think you guys get of how to add and subtract or multiply vectors. Sorry. To do a scalar multiplier. Okay. Okay, unit vectors and applications. This is a big one. The unit vector is defined as this. Okay, it's defined like that. So what this means is that your components will be like this. Need more space, hold on. Yeah, I know. I know. But trust me, with my messy handwriting, I'd really struggle with this in college. I know.
That looks like a
So what you're doing is you're downsizing. The unit vector is like downsizing the original vector. Yeah, like downsizing. Yes, go ahead.
When you introduced unit vector and zero vector, you said zero vector was like
Just a point. Just a point.
Unit vector was what?
Of magnitude of 1.
Oh.
Yep, magnitude of 1. So let's go down to example 4 so we can see this in action. So here's what you do, guys. You want you want to downsize it. So right now, what's my magnitude of this vector right now? Four plus 25. Correct. So my unit vector is going to be negative 2 over root 29, comma 5 over root 29. What was that, sorry? 3 squared? Negative 2 squared? 5 squared? 5 squared? My bad. So if I'm going 2 left and 5 up, here's the original vector. Okay, that's v. The unit vector is going negative 2 root 29, which is like a very small fraction. That's like, I don't know, negative 0.4 something. That's like 0.9 something. So it's going to look kind of like this.
It's just in the exact same direction.
Same direction, just shorter, with a magnitude of 1, yes. Same direction. Tiny little arrow going the same direction, it's just a portion of the big vector. So the downsize. There is a practicality for it, which I honestly cannot remember because I spent a long time since I've dealt with this stuff, but it is important to know because it does play some role down the road. I just can't remember when. So, but anyway, let's move on. So I'm going to jump around a little bit. Let me jump to, because some of these things are getting kind of repetitive. And I think you guys can figure it out. Let's jump to, remember I showed this other notation with I and J, same thing. Let's not worry about it. I'll scan these notes and put them in school just so you have them, but let's talk about example 7. Let's find the direction angle. That's important. Yeah, good. This is just like unicircle. Just like unicircle. Now, can I tell you right now, you can do tangent theta equals u2 over u1, or theta so in this case, -6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So over here, your angle is going to look like this. So that's totally going to be Pythagorean, sorry, unicircle type stuff. Sorry, not Pythagorean theorem, but tangent. Because what you could do is you could say tan theta equals -6 over 6. So if you think about the unicircle, right? If you're doing inverse tan of -1, where's that going to happen? At 3 pi over 4 or 135 degrees. Usually we like to say degrees for this stuff because that's just how we kind of measure things in real life. So yeah, that's 135 degrees for that one. So you have to consider what quadrant you're in too. Like what quadrant is B going to be in, by the way? Nope. 3, guys, right? See what's quadrant 3? Part B. Part B, sorry. I already moved on. Sorry, my apologies. I already moved on to part B. Okay, good. No worries. I was like getting a little worried. I was like, what? What's going on here? All right. Correct. So I'm gonna do tan theta equals I'm going 4 down, 7 left. Sorry. Yeah, that's correct. Yeah. I'll tell you right now, that's going to be 29.745 degrees. I have in my notes. I didn't do it in my head. But what is it truly? I travel how far and how much more? 209. 209.745 degrees, exactly. That's my angle. Exactly. Because you're in the third quadrant.
If you're less than 180, it's just your more, it's just whatever.
Oh yeah, I mean, so I mean,
I mean, just
what I'm doing is I'm doing a reference angle. I'm looking at this angle, really, to be honest, with the acute angle, and doing the tangent inverse of that,
and then
adding whatever I need to add, depending where I am. Exactly. So sometimes, like, they'll figure, like, oh, an airplane. I mean, airplanes actually use bearings, which I'm not gonna get into that today because I can't squeeze that in 3 minutes. That's another kind of like method of determining angles or direction. But let me show you one problem. Actually, shoot, I don't know if I could squeeze in one quick example really fast. Oh, Southwest. Good. Yes, your physics.
We did this last year.
Oh, okay. And Mr. Band's class? Oh, good. Great. Awesome. That shouldn't be too bad then. Good. All right. So, for example, this airplane. Guys, quiet. So, guys, thanks. So you want to find the component of the airplane. It's descending, whatever. So it's this thing, how many degrees? What's the angle? So what would that be truly? 210. So your vector would be like this: 100 times cosine, because cosine's horizontal. And sine is vertical. And then at this point, I trust you guys can do the calculation afterwards. I'll leave it at that. I'm not going to squeeze in example 10. We'll have to say that for another time. So, homework. You guys do the homework. I think you guys can handle the homework. Let's see. Yeah, it's on here. I might leave off number 13. Yeah, let me leave off number 13 because I need to kind of do that with you guys. Yeah, I'll leave off the last few problems. We could do that on Thursday. Okay. All right. We'll stop there for today, guys. I'll update schools right now.
Okay, how'd you do the?
No, I don't have to worry about that.